why use Lavaan? Why would you want to use Lavaan? If you're familiar with R, then Lavaan's not a bad choice. You know, you can live in the R world and you can do everything using Lavaan. In many ways, the mental model of it is very similar to Amos, and I believe things like M+ as well. The syntax is similar. I think it's the mental model of how the syntax is written is quite intuitive if you use if you're familiar with Amos and you're familiar with these tools. So in that sense, compared to some of the other R packages, it's a little bit more, I think, intuitive, and it also has a lot of features. So you don't hit the wall of, oh, I want to do this, and it can't do it as much with Lavaan. You can do special things for categorical variables if you have Likert type items. You can do growth curve models. There's a whole range of estimators and things like that. So there's lots of features that, you know, beyond the basic stuff. So if you invest in it, it's kind of worthwhile. I mean, in some respects, I would say if all you have to do is fit a really basic confirmatory factor analysis model, and you've got one model and it's 20 items, you know, use whatever you're familiar with. And Amos will probably be quicker for a lot of people, but if they like R, then Lavaan's not bad. I think where Lavaan is really great is in terms of reproducible research. You've got a script that you can point to and you can say, this is what I did. And it's awesome when you have a series of models, or really kind of models with lots of items. You can then start to see the benefits of managing that complexity with syntax, where drawing really, you know, if you've ever tried to draw an Amos diagram with 100 variables or 200 variables, and there's a hierarchical structure of factors, and it's like, oh my God, you know, it's a disaster. And then you've got 10 different models. So in those kind of slightly more complex cases, that's where Lavaan becomes really lovely. It also has, because it is R, you can sort of do some nice things where you pull out the fit statistics, just the ones you want, and you can quickly assemble a table of just the fit statistics you like. And that can be quite tiresome in Amos. Further things where it can be really nice is if you're trying to refine a model and you want to have some automated rule that says that if the modification indice is above this, I'll add this correlated residual. So there's ways of kind of automating that which aren't really available in tools like Amos. So yeah, it's a bit more of an advanced tool, but I think it's not, yeah, it's fairly intuitive if you're kind of using R and these kind of tools. Yeah. So yeah, as I say, hopefully you've got R and RStudio installed, and you've installed the Lavaan package by running, install packages Lavaan. I also today will use just the project template workflow. It's just how I like to do things, but pretty much everything I'm doing doesn't really rely on that, but that's just how I organize my files and folders, and I think it's quite nice. So if that interests you, there's I'm sure I just gave a talk last night on it, and so you could read up about it if you want. But, yeah, so in terms of getting started with Lavaan, the website's really nice. Yeah. This sort of statistician methodologist in Belgium has done a really good job of setting up tutorials and making the package fairly accessible. So there's lots of tutorials that will kind of take you through different kinds of models. So if it's a CFA or SEM and so on, it's really about going through the tutorials and trying things out and so on. The R help files for Lavaan are also quite good. So assuming you've got Lavaan loaded, The auto-completion for the main kind of models are fairly intuitive. So you can do things like question mark CFA, and you can learn about the arguments for confirmatory factor analysis and so on. I just pointed out these probably 3 help files that don't jump out to you immediately. We'll go into this in more detail, but if you want to get certain information from your model, like factor correlations or residuals or parameters, or anything that you want to know about your model, then there's this inspect argument, and that allows, there's a whole list of things you can pull out of it, and this just lists them all. Likewise, if you want to customize how your model is run, a lot of the options are sort of specified and explained with these Lavaan options. Anyway, and finally, we'll go into this in more detail, but yeah, there's also lots of what they call methods that you can apply to Lavaan objects to extract various information. So if you're familiar with R and say linear regression in R, you'll know that you fit the model and then you can extract summary statistics or various information from that. And so there's standard methods like coef to get the coefficients and fitted to get the values of factors and so on. Yeah, if you use it in a paper, make sure you cite the author's reference, because they obviously put in a lot of work, and they make it available for free. So the way of saying thank you is to cite. Yeah. And yeah, I've got some other CFA videos and lecture materials, both in general on CFA and then something a bit similar to this second exercise. It's already on the website. But there's also lots of stuff if you YouTube it. Cool. Okay, so that's all very abstract. So what I wanted to do now was give a very basic tutorial on the different functions in Lavaan, and then move to a more complex example, and then we'll go through an actual exercise. So just the way that this project template thing works is we run this first library project template load project, and I think I've already run it, so it's loaded a file called ccases from this data directory. So ccases is, well, it's just a data set. It's a personality data set. It's got 25 big 5 items. So hopefully familiar: agreeableness, conscientiousness, extroversion, neuroticism, openness. Yeah, so you can imagine, and I think in this meta.personality file we've got all the item information. So an agreeableness item is I am indifferent to the feeling of others. So, well, it's a negative agreeableness item, I guess. So that's just to say it's a standard measure of the big 5, and you would expect if you got people to do this test, and what have we've got 12,000 people who did this this test, and you can see the first few rows with head, and like one row is one set of responses to this survey. And I guess we would assume that if we were to factor analyze this, it would form 5 factors and so on. Yeah. So I just thought for this first example, it might be easier just to focus on 3 of the factors and imagine we're going to look at the first 3 items. So look at A1, A2, and A3, and C1 to 3, extroversion 1 to 3, and just make it really sort of concise so it's not too verbose. So how would we, say, fit a model to this data in structural equation modeling? How would we say there's 3 latent factors explaining these items, and they're correlated factors, and we want to fit a model? So the first step is to load the Lavaan library. I guess because I use project template, and this is not really what this is about today, but I would usually put it in here. But if you don't use project template, then you just would run library Lavaan, and that would make sure that you've got all the functions of Lavaan available to you. And if you weren't using project template, you could load some SPSS data like this. So you could use the foreign package and the function read.spss, and those kind of arguments will generally do a pretty good job of loading an SPSS file. So if you're not using project template, that's a way of getting SPSS files into R. This function just made the variable names lowercase. I find it much easier if I don't have to think about whether it's a capital E or a lowercase e or a capital A or a lowercase a. SPSS is not case dependent, so you'll often find you have variable names that are capital E, or is it lower, or is it capital, or some are capital and some are lower. So if you don't want to have to think about that, it's nice just to make all the variable names lowercase. So that's all that function is. Okay, so the model syntax of Lavaan is kind of like this. You have, if you're doing structural equation modeling and you're trying to predict one thing from another, then you use this little tilde, you know, above the tab key probably, or shift and above the tab key. If you want to say that you have items loading on a factor, you use equals tilde. If you want to correlate factors or correlate items for their residuals, you use double tilde, and occasionally you use this intercept command, but not too often. Okay, so what does that look like? So here's a really a basic, what they could call you've got 3 latent factors, and each latent variable has 3 items. So we're just doing a basic model here of saying 3 factors. Let's just look at 3 items now. And what this says is that we've got a latent variable called agreeableness, and it is represented by 3 items, A1, A2, and A3. And we've got a latent variable called conscientiousness that has 3 indicators, C1, C2, C3, and likewise extroversion, it's a latent variable, equals tilde. It says these following items load on it, E1, E2, E3. If you're familiar with Amos, you'll know that latent variables need to have a metric. There needs to be something that defines the scale that they are on. And the 2 ways to do that is either to constrain their variance to something, usually 1, or perhaps slightly more commonly, is to constrain the loading of the first item to be 1. So, yeah, that then, it doesn't affect the standardized loadings, but it will affect the unstandardized loadings. So by default, the Lavaan will assume that this first item has a loading of 1. And not that this example, actually, the next example will do it right. This example is actually, in some ways, an error, in the sense that you need to make certain that the first item is positively worded. Otherwise, you won't get agreeableness, you'll get disagreeableness. So technically, I think, if I remember, A1 was a negative item. Yes, I'm indifferent to the feeling of others. So it's actually a reversed item. So if I was going to be technical, I should probably call this disagreeableness, or better yet, I would rearrange the items to make sure that the first one in the list was a positively worded item. Well, maybe I'll do that right now. So I know how to comfort others. That's positively worded. So let's move that across. Oops. And C1, I'm exacting in my work. That sounds like conscientiousness. And E1, don't talk a lot. That's negative extroversion. Find it difficult to approach others. Know how to captivate people. That's extroversion. So we'll just move that one across as well. It's not going to affect the model fit or the correlation. Well, it'll just mean that everything's reversed. But yeah. Okay. So what we have here is the model. It's the model description. And essentially that's the syntax, and it's encased in quotation marks. So what it's doing is, if I run this, it's assigning that model string to the variable called model. And it looks like that. You may see these /n. So that is kind of a convention in R for new line. So /n means basically enter. And by default, it won't print like that. But if you put it in cat, it will print like you would expect to see it. It will replace the new lines with actual new lines. So if you want to check, oh, does it look right? You can put the model in cat and it will print out properly. Okay, so how do we fit a confirmatory factor and analytic model? And what does that look like? So Lavaan has a number of model fitting functions, and probably the two main ones are CFA and SEM. So if what you're doing is a confirmatory factor analysis, the main function is CFA. If you're doing structural equation modeling, well, then there's a function called SEM. The two main arguments are the model syntax and your data. So that makes sense that you've got a model syntax, and then we've got our data, which is a data frame with lots of rows and columns. So the variable names in C cases should correspond to, we should have variables called A1, A2, A3. And hopefully you don't, I'm not sure whether it will have an error if you have a variable called agreeableness literally in your data file. I'll have to check that. But definitely these variable names correspond to the variable names in the data. So yeah, just to reinforce that, yep, there they are, A1, A2, A3, C1, C2, C3. Okay, so you can just run that and you'll get something. Not much. Typical R style, if you run a model and you fit it, you don't get much output. So what we do is we assign that model fitting to a variable. So I often call the variable fit, but you could call it anything you like. So now we have the object. There's lots of things in fit, and there's lots of things we can get out of it. There are what they call methods that I guess apply to a lot of different R model fitting procedures. So summary is a common one. So if we do summary and fit, we will get a lot of the information we might want. So up the top we can see the number of observations in our data file. We can see that the model estimated correctly. It converged normally. If you have a poorly specified model, you could get issues. It's obviously an iterative fitting procedure, so eventually it converged on an optimal solution. You get what you might normally have seen referred to as the chi-square value. They call it the minimum function test statistic, but that's basically chi-square, so 172. So if you're used to reporting the chi-square in your confirmatory factor analytic models, you'd say chi-square equals 172 with 24 degrees of freedom, and it's significant. So here significance is technically a bad thing. It means that the model doesn't perfectly represent the data, but to be honest, the p-value is almost completely irrelevant in structural equation modeling, because if you have a reasonable sample size, you always get discrepancies between what your model is and the data. The question is it a reasonably good representation? And for that, we often refer to fit statistics, or we might compare multiple models and see, well, how much better is this model compared to some plausible alternative. Then you get what they call the unstandardized estimates. And to be honest, they're usually not as interpretable. Yeah, we're often more interested in sort of standardized factor loadings or the correlations between factors and so on. But you can see here that the first item was constrained to 1 in unstandardized terms, and you can see what the other loadings are like. And likewise, you can get the covariances, their standard errors, whether they're significant, and so on. So that's all fine, but probably what we really want is a few other different things. You can, if you look at the help for the summary method, you see that there's a bunch of other arguments that can be supplied to it. So you can sort of, there's a number of ways you can get fit measures and standardized estimates and so on. So for example, you can get standardized estimates by asking for them from the summary method by including. So this is the sort of the template of the summary thing, and you could add standardized equals true, or fit measures equals true, or anything like that. So if we do that, we get the, where are they? Standardized. Yeah, we get the standardized estimates, and I would assume it would be this STD all that's like what we would normally think of as the correlations and so on. So you can see, you know, agreeableness is correlated with conscientiousness at 0.26, agreeableness with conscientiousness 0.56. Yeah, so it's, I guess it's yeah, extroversion and agreeableness is a modest correlation. You could also check the factor loadings here. So, you know, are they above 0.3, for example, might be a definition of a reasonable item, and sure enough, they all are. Yeah. The other way of getting the parameter estimates is this parameter estimates function, which can be a bit nicer, I think. So it's just the parameter estimates. So you can use standardized solution to get the standardized loadings and correlations and so on. And a nice feature of this, particularly if you start getting very big models, like if you're modeling a 100-item test, you can have a lot of parameters, and you might want to just look at a subset. And so if you know about R's kind of ways of filtering, getting a subset, then it can be quite nice. So here I've saved those standardized estimates here in an object. And you can look at these symbols, or what's on the left-hand side or what's on the right-hand side. So if I wanted to just get the loadings, you can see that this OP variable has the kind of operator that's going on. So if I could say equals tilde, then this would just pull out the loadings. And that's kind of nice. So I could then go, okay, at a glance, are they, for example, I could go s.std would give them to me. And I could say, well, the abs, that's the absolute loading, and I could get the mean of that. And I could say, and that could be something you report in the paper, like the mean absolute loading was 0.61, and that's pretty good, you know. Or, you know, if you define 0.3 as bad, you can say, look, there's 0 loadings below 0.3. And I mean, you could do that visually on a data set this small, but if you had 100 items, this could be handy to be able to summarize features of correlations or loadings or all sorts of things. So yeah, that's where you get some nice features where you might not bother in Amos going through that process because it would be awful. But yeah. So likewise, you could get just the correlations. It's all just using different filter things. So that equals means equality. So where the operator is tilde tilde is correlations, and Actually, what have I done? No, this is the residual variances. But that's not what we want. Oh yeah, so that's the correlations, and that's the residual variances. Yeah, so anyway, you can extract the parameters and play around with them and get what you want, and then arrange them into tables. Probably a big thing that you're wanting to report would be, your RMSEA and your SRMR and all the different fit measures you might possibly want. So if you do fit measures on the fit object, you get, I think, all the standard fit measures you might want. You've got chi-square, degrees of freedom, CFI, TLI, RMSEA, SRMR, confidence intervals on RMSEA, etc. And one nice thing which I really like is often you decide, for whatever reason, by convention, you've seen the conventions of reporting, there are like these 6 fit measures you want. And in tools like Amos, you're kind of scouring through the output to get the ones you want. But you can just have them listed like this, and there you go. You've got just the ones you want, and you can see it in a glance, and that could go into your paper. It's just a bit more convenient. So yeah, in this case, we've got I guess a CFI that's sort of moderately good. I guess it's above 0.9, but not above 0.95. RMSEA is sort of okay, but not great. It's sort of below 0.08, I suppose, but not that much. And I don't know what SRMR is at 0.05 or something people often talk about. So, that's moderately good, I suppose. But that's kind of pragmatic, so I guess I'm kind of assuming some experience with those rules of thumb. And often it's more about model comparison, so by fitting a few different ones and saying, is your one better than an alternative? If you want to get more stuff, so there's lots of things you might want to know about a model. For example, you might want to get the variance explained if you were running a structural equation model. How much variance in something is explained. Or you might want to get some correlations between latent factors. Or you might want to get the observed correlation matrix or covariance matrix. So all that sort of stuff is listed and is available through the inspect method. So essentially you say inspect, you pass the object, and then you say what you want. And there's some special word which you put in quotations to get it. So for example, to get the R squareds, and not that that makes so much sense in a CFA context, but it's like the variance explained by the 3 latent factors in each of the items. So it's kind of related to their loadings, I guess. Probably it's the square of the loadings or something in this case. Then you can run inspect, fit, and then R2 or R squared. There's lots of things you can get. And yeah, if you go through this this help file, somewhere down here, details, you can see all the things you can possibly get. Some of them might seem a bit obscure, but yeah, if you look around, you'll generally be able to find the particular thing that you want. So for example, these are just a couple of common ones you might want. The sample statistics might be useful. So that's just the covariance of the data as well as the item means. So how much people agreed that whatever it was, item 3 represented. I know how to comfort other people. The mean was 4.5 on I think it was 1 to 6 scale. But anyway, sometimes you would want that sample data. There would be other ways of getting that, of course. You can also get the loadings and the correlation matrix, or this is unstandardized. So unstandardized loadings and covariance matrix in a more traditional form. And you can get standardized loadings and factor correlations as well in a more, in a matrix, or if you're familiar with factor loadings in traditional factor analysis, that's a bit easier to read than that standardized loading table before. So yeah, Another nice thing you can do is, particularly I think it becomes useful if you're fitting multiple models. So you can represent multiple models as just fit 1, fit 2, fit 3, but it can be quite nice to store them in a list, and then you can loop over at those models and extract fit measures. So just to give you a quick example, I've created an object called fits. It's an empty list, and that earlier model I fit, I've assigned to the first model. And another comparison model might be to sort of say that the factors are uncorrelated. So that can be done by saying orthogonal equals true, and that will give you uncorrelated factors. And you can even create new models by adding additional syntax to models. So if we have this, this earlier model, but say we wanted to allow a couple of items to correlate. Say we felt that A1 and A2 were very similar wording, and we wanted to allow them to correlate. So we could essentially add that to the bottom using the paste function. So you can see it's taken the existing model description and it's added a new line and the little extra bit down here. And so we could then fit that model and say, well, did that residual improve the model? And so where it gets really nifty is you have these sapply and lapply functions which are designed to loop over lists. And so essentially we can get, what this does is it kind of, it's essentially saying for each element in fits, and we've got 3 models, give me the fit measures. And I've just wrapped it around to give it 3 decimal places. So that gives us, we've got 3 models and we've got the fit measures. And you can see why I want to round that to 3 decimal places, because it's a bit difficult to read in scientific notation. And there's also still probably a few too many fit measures to be convenient, so let's do that. Hey, and now we've got, okay, that's something you could actually kind of, well, if it was a proper set of models, like something you might even put in a thesis or publish, where you got, okay, I've got 3 models, and we can say that when fit 0 was no correlated factors, the CFI improved dramatically by 0.11, RMSEA got a lot better, as did the SRMR. So definitely allowing the factors to correlate was important. And I can't remember if I chose those correlating A1 and A2 for a reason, but it seems to have improved things ever so slightly. CFI has gone up by 0.01, and yeah, I don't know. I can't remember whether I did it for a reason, but usually you'd have some justification that they were particularly similar items or something like that. Sometimes people like a statistical test rather than just sort of qualitatively comparing the CFIs. For, you know, there are rules of thumb about what's a meaningful or improvement of CFI and so on, but you can do a significance test to compare 2 models. So this is saying that, I guess, adding correlated factors, so 2e to the negative 16, so that's like a p-value 0.0000, lots of those, and then eventually there's a 1. So very much significantly improve the model. So that's often useful. Yeah. You may be thinking about how to improve models as well. As you move along, you may be thinking, oh, I haven't got a great fit. Is there a way to improve things? And 2 ways of doing that is to look at the residuals, so to see what aspects of the model are not captured. Another way is modification indices. So you can get the residual covariance matrix. Probably the residual correlation matrix might be a more meaningful metric. So this is essentially saying, to what extent is the correlation between 2 items not captured in the data? So I think this is saying that, say, the correlation between C3 and A2 is is 0.14 larger than is implied by the model. So that's sort of, compared to the others, which are more like 0.01, 0.04, you know, that's a fairly large deviation. So you could even look at that. I mean, we could look at that right now and say, okay, well, what is it about C3 and A2 that is there something, I haven't looked at this before, so I'm kind of curious if it makes any sense, but do things according to a plan and inquire about others' well-being? I don't know. Nothing's jumping out at me. But maybe there's some logic to it. I don't know. The other option is to, so that could potentially be a correlated residual you add to the model. Another option is to add modification indices. To look at modification indices. So these are essentially tell you if you add this parameter, it will improve your model by this amount. So the function is called modification indices, and you just give it the fit, and you get this huge list of all the possible modifications you could make. So, for example, you could add cross-loadings. You could load item C1 on agreeableness, or C2 on agreeableness, or A3 on conscientiousness. There's all the possible cross-loadings. There's all the possible correlated residuals. So you could correlate A3 with A1, or what was the idea? A2 with C3. You can see it's moderately large in this case. Usually there's theory constraints which say what would be inappropriate. In particular, correlated residuals within a factor are often seen as more legitimate because it's like, oh yeah, you just happen to have two agreeableness items that are very similar as opposed to the normal level of similarity. As a general kind of point of practice, people usually add modification indices if they are above a threshold. So they try and want to look for the particularly large ones. And by default, it seems like it's ordered by, you know, the variable name and maybe the operator or something. So it can be nice to order it by which ones are the biggest modification indices. So you'll see here, this essentially is a way of ordering it by the modification indice in a decreasing order. So now we have the biggest modifications at the top. So they're the potential ones you might want to add. So A3 and E3 supposedly are candidates, or E1 and E2. So let me give it one more try and see if it actually makes any sense. So usually these big ones, you'll be able to look at them and you'll say, oh yeah, that makes a lot of sense. So E1 and E2 don't talk a lot, find it difficult to approach others, know how to captivate people. So in this case, maybe it's picking up on some method effect related to reversed items, that two negative extroversion items were slightly more similar than the other third one that was not. And now you can enclose it in a head, which will just give you the first, say, 10 modification indices. Or, you know, you could extract just the ones above 10, you know. So yeah, there's all sorts of ways of doing that, and then you could then add anything you felt was theoretically appropriate to your model as a final additional model. So for example, you could basically use the procedure up here to so we could call it model 3 and fit 3, and we could add I don't know, maybe E1 and E2, and make sure that this set's model 3. And then somewhere maybe we'll rerun that fit line that did it all nice and pretty. And sure enough, fit 3 has improved the chi-square. Hopefully, it should be 172 minus 132 should equal the modification indice. At least if you're adding only one additional term. I think that's what it should be equal to, but we would see, I guess. Yeah, so that's led to quite a substantial improvement in CFI and RMSEA and so on. A final thing you might want to do is actually save the latent variables. So if you wanted to use this latent agreeableness variable, add it to your data set and do some other stuff, you can use the predict method. So that's essentially giving you a data frame with all those latent variables. So that was agreeableness, conscientiousness, and extroverting. So that's people's score on that, and you could then add that to your data set. So you could bind those columns so you've got C cases as your original data set, and then you've got these new saved scores, and you could create a new data set that has now they're added in, and you could do your normal analyses using normal analyses in R. You could get the the correlation between I don't know. This is pretty. Maybe we could plot it. Anyway, that's not how you get it. That's not how you get a correlation to its core. But anyway. Oops. So, that's not a beautiful plot. It's a bit cramped, but the point is you can use those variables for normal analyses then. I'll just quickly show you SEM. I'm not going to spend much time on that, but if you wanted to actually predict something, let's maybe try and predict these latent variables, agreeableness, conscientiousness, and extroversion from age and gender. So I've just made gender a numeric variable where 1 is male and 0 is female. So what we have here is we have the usual stuff, 3 latent variables, agreeableness, conscientiousness, and extroversion. And now we've got what makes an SEM now is we've got this single tilde. We're going to predict those 3 variables from age and gender. Normally, probably if you're bothering with SEM, you probably have 1 latent variable predicting another, and you can do all that. So, but I just thought this would be a simple example. Instead of using CFA, we use SEM, and we give it the model, string, and the data. And yeah, we can look at the unstandardized parameter estimates. This is showing just the regression ones, and so we can, I'm not entirely sure of the metric of these variables, so unstandardized is a little kind of fuzzy, but it's certainly showing significant effects across the board. And I guess we could use the standardized, and you could see that 1 standard deviation increase in age, whatever that is in this data set, leads to a slight increase in conscientiousness. Almost 0.1 of a standard deviation. Males are, we probably want to get the metrics right. There's a 1 standard deviation increase on genders. It's probably a bit like moving from females to males, but yes, slightly less conscientious, older people slightly less agreeable, males more agreeable, older people less extroverted, males slightly more extroverted. Don't know if that's interesting. Okay, final thing I'll show, you can, I haven't played around with this much, but it seems like if you're used to the nice graphical diagrams of AMOS, there is a way of getting that with package called Simpler, and let's maybe make this as big as we can. So there is a way of getting something like that that shows, age predicting the 3 latent variables, the indicators, and if you zoom in really carefully, you can actually see the numbers. And I guess these are something to do with whether they're negative or positive loadings and whether they're significant or above a threshold or something. To be honest, I haven't played around with it too much, but yeah, it seems quite nice.